be Marco, and he's going to give a mini course about the isoperimetric problem on manifolds with lower curvature bounds.
Okay. Thank you very much, Raquel, for the introduction, and thanks to all the organizers for the invitation to give this mini course. Unfortunately, I couldn't be there this very week, so maybe it will be for the next time. But anyway, thank you very much. I'm happy to give this mini course for you. So the target of the mini course is the one of students, PhD students, and young people. So especially for the lecture of today, is going to be a very friendly introduction to the topic of the isoperimetric problem on manifolds. So I hope that the experts will not be too bored, but I promise that in the next two lectures, we will see something that is closer to the modern research. So for today, in lecture one, introduction to isoperimetry, isoperimetric problem, and very basic stuff. So lecture one. So here is the setting. For all the course, this is going to be our setting. We will always consider MG a Riemannian manifold, which is complete, and if you want, without boundary. Not very important, but if you want, think of it without boundary. And if you want to think of it as a non-compact manifold, because most of the problems will arise when the manifold is actually non-compact. Now, once you are given a Riemannian manifold, you can define the Riemannian distance. So D is always going to be our Riemannian distance. And capital N is going to denote the dimension of M, which is assumed to be greater or equal to 2. Finally, a last ingredient we can define once you are given a Riemannian manifold is the volume measure that I'm going to denote with this symbol, meaning that when I write absolute value of a set A, here I am measuring the volume of A, right? So more precisely, this is the Riemannian volume measure. So in particular, it is that thing that if you look at it, if you write it in a local chart, it is the square root of the determinant of the matrix times the Lebesgue measure. If you know something about measure theory, in particular, the Riemannian volume measure coincides with the n-dimensional Hausdorff measure that I will denote with the symbol. And okay, this is for the setting. Now we are going to study the isoperimetric problem, right? So we need to define, first of all, our favorite energy for this mini course. Our energy, the isoperimetric problem is going to be a variational problem. We want to minimize something, and the energy that we would like to minimize is the so-called perimeter. So perimeter is the first thing I want to define. So what is the idea behind the definition of perimeter? Well, the idea is the following. We would like to give a weak notion of the area of the boundary of a set. If I give you a set E with smooth boundary, for example, and by smooth I mean that, for example, the topological boundary is actually a compact, say, smooth submanifold of my manifold E, so I am thinking that E is contained in M, the area of the boundary of E is just the n-1 dimensional volume of this submanifold. But in order to study a variational problem, we all know that it is, one prefers to have a weaker notion, something that works well with compactness and lower semi-continuity properties. So we need to define a weaker notion. And here is the definition. The definition is the following. If I take E containing in M, for example, a Borel set, and we will always consider in this course sets with the finite measure, even if it's not too restrictive. I want to tell you what is the perimeter of a set E inside an open set A. So let's fix also A containing M open. And the quantity I want to define here on the right is basically the following idea. Here is the set E. This is the boundary of E. For example, this is my open set A, and the perimeter of E inside A should be the number, that should be the resulting number if I want to compute the area, the n-1 dimensional area of E inside that set, that open set A. And the definition is given by a relaxation procedure. It is the following. I take the infimum of the lim-inf over I, integral over A gradient ui, the measure, among all sequences ui locally Lipschitz functions over A converging to the characteristic function of E in L1 lock over A. So now I will try to give you an intuition behind this, this formula. But what it is telling you, it is already a quantity that is going to be automatically lower semi-continuous, right? Because this is a typical relaxation procedure. Relaxation. So the resulting function is automatically going to be lower semi-continuous. And in this sense, I am happy if I want to do calculus of variation with this functional. And now I would like to try to convince you that this is a good notion for measuring actually the perimeter of a set. And here is the reason. Of course, maybe for to be more comfortable, I will define perimeter of E, the perimeter of a set inside the whole ambient manifold M. And if the perimeter of E is finite, then I will say that E is a set of finite perimeter, just to fix the terminology, set of finite perimeter. And by the way, this definition by relaxation, if you want, this weaker definition for the area of the boundary of a set goes back to the original works of Cacciopoli and De Giorgi around the 50s. Now, as I said, I wanted to try to convince you that this formula actually gives you the area of the boundary of something. And here is the idea. Imagine that here is your set E, okay? I draw it like this because next I can draw the characteristic function of my set E. This is the characteristic function equal to 1 here and 0 out. And let's say that imagine that the boundary of E is smooth. Whenever I say that the boundary of a set is smooth, I mean that it is actually a smooth submanifold, right, of the manifold. And imagine that I want to approximate the characteristic function of E by a sequence of locally Lipschitz functions, and I want to infimize, I want to pay the least possible L1 norm of the gradient of these approximating functions. So I can believe that the the smartest way to approximate the characteristic function of E is by taking a sequence like this, right? I take UI, my sequence of locally Lipschitz function like this, and then I approximate better and better in L1 the characteristic function of E, right? So for example, I can believe that the distance here where there is the slope of UI, for example, is of the order 1 over I, and the modulus of the gradient of UI here is of the order I, right? And so if I integrate over M the gradient of UI, then actually I am integrating something of the order I here on this tubular neighborhood, right, of the boundary of E. So approximately what I get is I times the volume of that neighborhood, that more or less I can believe is of the order area of the boundary of E times 1 over E, right? So in the limit, I approximate area of the boundary of E, right? If you believe this. Okay, so this is more or less the intuition behind the formula. And this turns out to be a very useful definition for this function, as it is already lower semi-continuous already by definitions. So this is the definition done by relaxation, and we think of it as a generalization of the n-1 dimensional measure of the boundary of a set. Now, a few remarks about this definition. First remark, of course, in case E is smooth, meaning that the boundary of E is a smooth submanifold, then of course this weak notion of perimeter agrees with the usual notion of n minus one dimensional volume of this submanifold that is the boundary of E. So it agrees with the, should agree with the classical notion. Next, something that is going to be very important for our variational problems is that we have a compactness plus lower semi-continuity property for this functional. It means the following. Let's say that you have EI, a sequence of subsets of M, and you know that the supremum over I of the volume plus perimeter of EI is uniformly bounded. Then, so in particular, you have a sequence with equibounded perimeter and equibounded volume. Then, up to the subsequence that I do not write, you can say that EI converge to some set in M in L1 lock, and the perimeter is lower semi-continuous. So the limit of the perimeter of EI is greater or equal than the perimeter of E. Okay, up to subsequence. And when I say that a set converges to another set in L1 lock, of course, I am thinking of the characteristic functions, right? EA going to characteristic function of E in L1 lock over M. Okay, so these are the two most basic properties. Now I want to give you two more properties. And one is the following observation, that the definition we gave of P, the definition of the perimeter as a functional, if you look closely to the definition, actually it depends, the definition of P only depends on the presence of the Riemannian distance and of the volume measure. It depends ultimately on the presence of the Riemannian distance. What do I mean by this? If you go back to the formula, here I need to approximate a function in L1 log, so I need a measure on the space, and here I am integrating with respect to that measure the modulus of the gradient. But now, if you want, here is the fact that the modulus of the gradient of a function at some point x is actually the lim sup as y goes to x of y uiy minus uix over the Riemannian distance x, y. This, let's say, for almost every x in M, right? Because it is a local elliptic function. So by Rademacher theorem, this is a function that is almost everywhere differentiable. And of course, if I am on M and I want to compute the modulus of the gradient here, let's say that the gradient is this vector here, then I can approximate, I can take the limit of the difference quotient approximating the direction of the gradient of U, and then I will get the modulus of the gradient. But now, in the definition on the right, there only appears the distance, right? There only appears the distance. So if you want, this quantity, the modulus of the gradient at a point, is only dependent on the presence of the Riemannian distance. And also, I said that the second ingredient we needed is the volume measure. But if you believe me, if you believe what I said at the beginning, this can be represented as the n-dimensional Hausdorff measure of the manifold, which is taken with respect to D, right? To define the n-dimensional Hausdorff measure, you only need the Riemannian distance. You only need a distance, right? So eventually, you only need the distance if you want to give this definition of perimeter. So eventually, the moral of this observation is that actually P as a functional is well defined only if I considered M endowed with a distance, the Riemannian distance in this case, and with the n-dimensional Hausdorff measure, that is the volume measure I am considering. So this will be more useful in the next lecture, but the moral is that we can more or less forget about the smooth structure over M, and just remember that M is coupled with a distance and with a measure, which makes of M, if you look at M as given by this tripole, is something that we call the metric measure space. Metric measure space. Again, this will be more useful in the next lecture. We will only see smooth manifolds today, but just remember that we have a good definition only if I give you the distance and the corresponding Hausdorff measure. This is actually the intuition, by the way, just to quote somebody. It is the intuition behind the definition and the study of perimeter and more generally BV functions on metric measure space. There is today a well-established literature, starting, for example, from the works by Ambrosio and Miranda around 2000, okay, where they started looking at this definition as a relaxation and to all its consequences. Okay, so this is the second remark about the definition of perimeter that we will remember for the next lecture. The final observation I want to make is a formula, a very useful formula that is called the coarea formula. Coarea formula. So what is the coarea formula? It is a nice, if you want, integration formula for computing the integral over a manifold of the modulus of the gradient of a function. Let's say that f is locally Lipschitz, for example, okay, over m. And then the formula tells me that the integral of the modulus of the gradient is the integral from minus infinity to plus infinity of the perimeter of the super level set f greater than t in dt. Okay, and maybe at this moment it could be not clear why this is useful, but I will show you an application in a few minutes. So these are all the very basic properties of this functional called the perimeter. Now, now we move on, and we are ready to define the variational problem that eventually we want to study. So the isoperimetric problem. Isoperimetric problem. So what is the definition of the problem? It is the following definition. Always my setting for the moment is going to be a smooth Riemannian manifold as before. And the problem is the following. Given V, that I think it's a number between 0 and the total volume of M, and I think of it as a volume, then I want to study, which is a general word for saying understand whatever you can about the infimization of the following quantity. So the following variational problem. I want to minimize the perimeter of E among subsets of M having fixed volume equal to V, right? So the very basic idea is the following. I assign some volume that my sets must contain, and the question is it possible to rearrange the mass of this set, giving you the least possible area of the boundary? That's the very basic question. Now, what does it mean study? Study means everything you want. So the most basic question is about existence, right? So existence means, is this infimum actually a minimum? And in such case, if, for example, E is a minimizer, so is a minimizer, so it has some volume V, it minimizes the perimeter among sets with the same volume, then we say that E is an isoperimetric set. So this is the first question you may ask. Is it possible to prove existence for some volume, for a given volume, for any volume, small or large volume? And after that, you may have many more questions. Like what can you say? What can be said about isoperimetric sets, but also what can be said about the value of the infimum. The value of the infimum has a name that I'm going to define now. So the value of the infimum, I can see it as a function of the volume, right? And I will denote it with this symbol, Im of V. And this is a function called the isoperimetric profile. So a question could be, what can be said about the isoperimetric graph, but also what can be said about the function Im. So more precisely now, also defining, for example, Im of 0 equal to 0, and Im of the total volume of M equal to 0 in case the total volume is finite, okay? So from now on, I will define Im to be the isoperimetric profile, right? So like this here, if you want to positive values, define Im to be this function of one variable, so function of the volume assigned to every volume, the infimum of the problem. This is called the isoperimetric profile, as I said before. All right. Okay, so these are the ingredients and the basic question you may ask about this isoperimetric problem. And now, in the remaining time, I want to try to give you some example and some intuition about the very basic facts about this isoperimetric problem. So I want to start with some examples, some very basic examples one should remember. Examples. Now, for example, I may want to study the isoperimetric profile for the most beautiful manifolds that I could think of, right? So, for example, the first thing I want to do is try to solve, for example, the problem of existence of isoperimetric sets on the so-called models of constant curvature, right? So they are Rn, for example, the sphere of radius 1, and the hyperbolic space of dimension n, right? So, for example, these are, you know, the simply connected manifolds of constant curvature equal to 0, to 1, and to -1. And I can ask, is it possible to solve the isoperimetric problem here, for example, the existence? And the answer is today, of course, well known. Of course, in Rn, probably everybody here knows that balls in Rn are isoperimetric sets, but the same conclusion also holds in the sphere and in the hyperbolic space. So if I am interested in existence, well then, yes. So for any, let's say, admissible volumes, okay, of course the sphere has finite volume, the other two spaces, but okay, it doesn't matter. So for any volume admissible here, there exists an isoperimetric set of that volume, V, and it is a ball, so a geodesic ball. So in particular, on if you want, on the sphere, if I take a pole, all the possible spherical caps of a given volume are isoperimetric sets for that volume. Okay, so I am happy with that. Now, I don't know, maybe a spontaneous question could be, so is it always true that balls are isoperimetric sets in the general Riemannian manifold? But of course, the answer is definitely no. But the answer here is more dramatic, because it may also happen that on a Riemannian manifold, you have non-existence of Riemannian manifold. So the question of existence is completely non-trivial, actually. And I want to comment a little bit on this. So this is the problem of existence on the models. And about the existence, we immediately have two possible situations: the situation of a compact manifold and the situation of a non-compact manifold. And these are completely different, because if you are interested in existence, then on a compact manifold, you are done. So this is the second example. If Mg is actually compact, then for any, again, admissible volume, you have existence of isoperimetric sets of that volume V. Why so? Because of the fundamental property of compactness and lower semi-continuity of the perimeter that we mentioned before, right? You just argue by direct method. If this is your compact manifold M, you take a minimizing sequence EI for the volume you are interested in. So the volume of EI is constantly equal to V, and the perimeter of EI goes to the infimum of the problem at that volume. But then you have a an equibound on the volume and then equibound on the perimeter, and then for sure this sequence has a subsequence converging in L1 lock, but the manifold is compact, so L1 lock is equal to L1, and eventually this is going to converge to some limit set E, which need not to be a ball, not at all, on a general Riemannian manifold where you have no symmetry, but for sure you have L1 convergence, so the volume of V is going to be V, and you have lower semi-continuity of the perimeter, so the perimeter of V is going to be equal to the profile at that volume V. So E is going to be isoperimetric just by applying direct method. Direct method means exactly the following: to take a minimizing sequence and see what happens, see if you are able to prove that it converges to a minimizer. And so you immediately understand that the problem becomes non-trivial the moment you are considering a manifold that is non-compact, right? So because, for example, if my manifold M is non-compact, in principle, what could happen? It could happen that if you argue in the same way, you take your minimizing sequence EI, it can happen that maybe to arrange in the best way this quantity of volume V, it is maybe convenient isoperimetrically for the set to go towards infinity, to slide away towards infinity. So in the limit, you see nothing, right? I want to convince you in this way. In principle, this could happen already in Rn if you don't know that balls are isoperimetric, right? Even if I take Rn and let's pretend that I don't know that balls are isoperimetric, I can take a sequence of balls translating towards infinity. This is a minimizing sequence because every ball here is actually a minimizer, but in the limit, in the L1 lock limit, I see nothing in the limit. So I cannot conclude on a non-compact manifold by direct method that I have existence or non-existence. And okay, so this is the main enemy we will try to deal with in the next lectures, actually. And to conclude this speech about existence, by the way, today we have results saying that sometimes for some volumes on some manifolds, you actually can prove non-existence of isoperimetric sets, precisely because of the reason, because it is isoperimetrically convenient for a set to go far away towards infinity. I want to state it as a final example, and the moral of the next example is to tell you that you can have non-existence of isoperimetric set no matter the bound on the curvature you are assuming. So what I mean is the following. Before I had, I had Rn that is flat. Then I had the sphere that is the most beautiful example of a manifold with the positive curvature, and I had the isoperimetric, the hyperbolic space that is, if you want, the most beautiful example I can desire of a manifold with a negative curvature. But now I want to state that there are results telling you that in both cases, so either if you have positive sectional curvature or negative sectional curvature, but non-constant, okay, of course, then it may happen that for some volumes there is a non-existence of isoperimetric sets. So in the case of negative curvature, this is already a classical result. So the example tells you the following: there exist manifolds with no isoperimetric sets for all or for some volume. Let's say for at least one, for some volumes. And we can give, as I said before, we can give examples both in the non-positive and in the non-negative curvature situation. The non-positive case, so curvature, let's say less or equal to 0, is already something well understood in a work by Ricci, for example, in 2001. Where basically you can construct a manifold with it is a warped product, so it is you have a radial metric with an increasing curvature, always less than or equal to 0, and you can say very explicit that it is convenient to go away from any compact set to minimize the value of the isoperimetric profile. But just to give you a very explicit example, actually, to give you a very, very explicit example in this situation, you can take, for example, as a manifold, the graph of this function, the graph of the function x squared minus y squared in R3. You think of it as a submanifold of R3, but then you set the isoperimetric problem on M with the induced the Riemannian metric, right? And it is not obvious, but you can prove that it is convenient already on a simple manifold like this. It is convenient for a minimizing sequence to go towards infinity. Okay, and this is for what concerns the non-positive curvature case, where then here the thesis is non-existence of isoperimetric sets for any volume, while in the positive case, here I can also make the strict inequality, by the way. In the case of positive sectional curvature, there is a very recent example, actually a family of examples due to Antonelli and Glaudo. It is a preprint appeared, I don't know, 1 month ago, something like that, where they give examples. They construct manifolds MG with a non-negative sectional curvature, actually strictly positive sectional curvature, but with non-existence of isoperimetric sets for some volume, for small volumes specifically, for small volumes. So the moral of this example is, okay, no matter what is your favorite upper or lower bound on the sectional curvature, it can happen that you have a non-existence of isoperimetric sets. And this could be a problem in attacking, you know, further questions on the problem. So, okay, this is an overview on the definition of the problem, on some examples on Riemannian manifolds. And in the remaining time now, I would like to discuss another thing strongly related to isoperimetric problem, that is the validity of the so-called isoperimetric inequalities now. That is, again, you know, a word heard many times, but I never mentioned it for the moment. So the last topic for today is isoperimetric inequalities. We will see at least 2 isoperimetric inequalities in the rest of the course, but now I want to discuss the simplest one, the most classical one, that is the isoperimetric inequality in Rn. Now, what is an isoperimetric inequality, by the way? So the idea behind this word is the following: to give a lower bound on the perimeter of any sets. So more precisely, to give a lower bound on the function isoperimetric profile. So if I say that isoperimetric profile is greater or equal than some function of the volume, then in this course I will call it an isoperimetric inequality. Now, most of the times we will see isoperimetric inequalities of a specific kind that are of the following form: isoperimetric profile at a volume V greater or equal than some constant that I will denote like C iso, the isoperimetric constant, some constant such that the inequality holds, times volume to the power n minus 1 over n. This is a very common power that you can find, especially when you study non-compact manifolds. And the first example of such an isoperimetric inequality that I want to show you is the one on Rn. Maybe many of you already know this inequality, but anyway, I want to recall it. So let's say that now Mg is Rn with the Euclidean metric, the standard metric. Well, then you have the following isoperimetric inequality: the perimeter of any set E. Of course, I can give a lower bound on the perimeter of any set in terms of its volume, right? Then taking the infimum over the sets, I get an isoperimetric inequality of this type, right? So perimeter of E is greater or equal than n omega n to the power 1 over n volume to n minus 1 over n for any E contained in Rn, let's say with finite volume, It's the isoperimetric inequality in Rn. Moreover, the equality is achieved if and only if E is exactly a ball of the correct volume, is a ball, right? So as I said before, this inequality actually has this form above, right? If you call the volume of E, you call it V. Here you have the perimeter of a set of volume V. I take the infimum over sets of that volume, and here I get isoperimetric profile of that volume, right? So this is actually of that form, and they writing inequality in these two ways is equivalent. This is the sharp constant on Rn. Indeed, we can have equality precisely, of course, precisely when E is one of the possible isoperimetric sets for some volume, so precisely a ball. N is the dimension, and omega n is the volume of the unit ball in Rn. Okay, omega n, standard notation. And so today there are so many proofs of this theorem. But since this is a course, I would like to mention to you a possible proof. I give you a sketch of the proof of this inequality, only of the inequality, not of the rigidity. And the proof I would like to present to you is a proof given by Cabret. One of my favorite proofs is one of the simplest one, given by Cabret, published, if I'm not mistaken, in 2000. And it is interesting also for this conference, the following proof, because okay, here we are in Rn, but the conference is about Riemannian manifolds, right? But it is interesting to notice that the proof that I'm going to present to you, that it is based on a method that is called the ABP method, where this letter stands for Alexandrov, Bachelman, Pucci. It is a method that currently has seen a lot of improvements and generalization on Riemannian manifolds. So this is what I wanted to just to mention to you. There are adaptations of this method. So method also on manifolds. And for example, there are remarkable papers by Brandle, very recent, 21, 22, probably. You can look for them. And so what is this method? This is a very simple proof. Let's consider E containing Rn with finite measure, and for simplicity, let's say that E is also smooth. So smooth. Okay, then one can argue, you know, by density to get the inequality for any Borel sets, but we don't care about regularity today. So E is smooth and it has a finite volume. I want to prove this inequality, and the idea is to set up a PD and to use in a very clever way the solution of this PD. I solve the following problem: Laplacian of U equal to perimeter of E over volume of E inside E. Let's say that E is open in my mind, while I take the boundary condition that the exterior, the normal outer derivative of U is equal to 1, right, on the boundary of E. And I solve this problem. Of course, I get a smooth solution because E is smooth. And the key observation is the following: that I leave this observation to you as an exercise, but then I will give you the idea of how to prove it. But it's not difficult. The key observation is the following: you look at the map gradient of U, and you think of this map as a map from E into Rn, because that's what it is, right? The gradient. And the observation, so the exercise, is to prove that if you take the image through the gradient of the points in E such that the Hessian of U is non-negative as a matrix, right? Well, then this covers the unit ball in Rn. Okay, so the image of these points covers the unit ball. What is the idea? Why should this be true? The idea behind this is actually very, very simple. Let's think of this problem as in one-dimensional approach, one-dimensional picture. One-dimensional picture. The picture is the following. In this case, let's say that this is my manifold or the real line. Here is the set E, and now I want to plot the graph of U. Now, in one dimension, or if I want to cheat a little bit, here, you know, the Laplacian is non-negative. So let's think of this U as a convex function, just to to be very, very simple. So I can think of the graph of u like a function like this, right? Where the normal outer derivative is 1. So here is 1, here if you want is minus 1. And this is the image I can think of the graph of u, right? Now I want to prove that a vector v in the unit ball is inside this set. So I select v in the unit ball. It means that its modulus is less than 1. And then together with the graph of u, I can plot also the graph of a generic affine plane whose gradient is v. So this is the graph of a function of this form, like alpha plus scalar product v times position vector, right? So this is a plane, and its gradient is exactly v. And if I change alpha, then I slide this plane up and down, right? And the important thing is that since I have chosen v with modulus less than 1, this plane is not too vertical. It's not like that. It's not too vertical. In particular, it has a slope which is less than the slope at the boundary. So if I start from alpha minus infinity and then I increase alpha, I increase my plane, there will be exactly a point, exactly a value of alpha such that I touch with this plane the graph of u inside E, not on the boundary of E, but inside E. So precisely, I'm going to touch the graph of u at a point where the Hessian of u is non-negative. And since I'm touching at such point, and since I am touching at the interior of E also, the gradient of u here is going to be equal to the gradient of this plane, which is exactly v, right? So at this point, I'm going to touch at a point where the Hessian of u is non-negative, and here the gradient of u is going to be equal to v. And so eventually I've proved that for any v, I can find x like that, such that v is reached by the gradient computed at that point. So this is the key observation. Once you have this key observation, you can prove the isoperimetric inequality. You can prove the isoperimetric inequality simply by a change of variable, because I can start with omega n. This is the volume of the unit ball in Rn. And so by the observation above, this is less than or equal than the volume of the image of that set, right? Of that set through the gradient. But now this is less than or equal by a change of variable formula of the integral over the set where the Hessian is non-negative of the determinant of the Hessian of u. This is just by a change of variable formula, right? And I don't need to put an absolute value here because I am exactly on the points where the Hessian is non-negatively defined, right? But now, exactly because I am on this set, if I think of this determinant as the product of all the eigenvalues, I can apply the fact that the geometric mean is less than or equal than the arithmetic mean. And so in the next step, I still integrate on the set where the Hessian is non-negative, but in place of the determinant, I can find the Laplacian of u over n raised to the power n, right? Because in the geometric mean, I would need 1 over n here, right? So geometric mean, arithmetic mean inequality, I get this, but now I use the PDE. In the PDE, I said that the Laplacian of u is constant. It's constant perimeter over volume. So here is just less than, integrating over all the set, perimeter of E over volume, there is also an n, to the power n. And if you just rearrange the first term here with what we obtained, this is exactly the Euclidean isoperimetric inequality. Okay, so this I wanted to show you, and maybe in the last 2 minutes, if I may, I want to give you a final motivation of why to study this problem, because in my opinion, it is already nice. If you like calculus variation, it is already a nice problem. But maybe to convince younger people, I want to tell you a functional aspect of this problem. Functional functional aspect for this problem that it's simple and really interesting in my opinion, and it relates functional analysis with the isoperimetric problem, and more precisely functional analysis with isoperimetric inequalities. So in the next statement, I'm exactly going to tell you that isoperimetric inequality is equivalent to a typical inequality you see in functional analysis, that is the Sobolev embedding, the Sobolev inequality. So the title of this theorem is isoperimetric, isop, if and only if Sobolev. So if you think that Sobolev inequality is useful, then the isoperimetric problem is useful in a sense. This is how we sell it. So this is, by the way, an observation, if I'm not mistaken, due to Federer and Fleming. Federer and Fleming. And the statement is the following: the validity, that there is always a manifold behind, it's our setting. The validity of an isoperimetric inequality, so a generic one with some constant, P of E greater or equal than C iso for some constant times E n minus 1 over n for any E inside M of finite volume. Well, this is equivalent to the W11 star Sobolev inequality in the following sense: if and only if C iso of integral over M f n over n minus 1 over n is less than or equal than the integral over M of the gradient of f for any function, let's say locally Lipschitz and L1. So, okay, so the moral again of this statement is Euclidean. This is a Euclidean type isoperimetric inequality is equivalent to the validity of the Sobolev embeddings, and again, this is very easy to prove. Very easy to prove. Why? Because the arrow from right to left is just by definition. By definition. Why? Because in place of f, I take a function ui going to the characteristic function of E, as said in the definition of perimeter. So this goes in L1 to the characteristic function. So on one side, this brings me to the perimeter of E, because I am right in the definition of the perimeter, and on the left-hand side, this goes to the volume of E raised to this power that ends up here, exactly. So in this way, it's just by definition. So by the way, I'm almost done. I wanted to tell you what happens for the other arrow, that is more the one I am interested in, right? Because I am studying the isoperimetric problem. I want to tell you what I can get out of the problem. And it is precisely in this arrow that we will use one of the remarks said above, that is the coarea formula. And it is just an application of coarea, because if I start computing the integral of here on the right-hand side that I want to estimate from below, this by coarea here, so I am using exactly the formula I told you above, by coarea, this is going to be the integral from minus infinity to plus infinity of the perimeter of the super level set, right, in dt. And now I can use, because by assumption I have it, I can use my isoperimetric inequality. So this is greater or equal than C iso integral from minus infinity to plus infinity of the volume of the super level raised to the power n minus 1 over n in dt. Now it is interesting because now we can apply a very basic inequality in real analysis. Again, I leave the next inequality to you as an exercise, but there is no theory behind this inequality. Just real analysis. You can estimate from below this integral in the following way. The constant is always C iso, and here it appears the integral from minus infinity to plus infinity of n minus 1 t to the power n over n minus 1 minus 1 and the volume of the super level set in dt raised to the power n minus 1 over n. So this is an exercise that is only based on the fact that you just need to use that that n minus 1 over n, you can think of it as 1 over alpha for some alpha greater than 1. And you just need to notice that this function is decreasing with respect to t. Whenever you integrate something like that, a function g of t decreasing to a power 1 over alpha with alpha positive greater than 1, then you can conclude this inequality. But look at what happened now. Now I moved this power out of the integral, and here I have the volume of the superlevel, and here I can recognize exactly the layer cake formula for the function f to the power n over n minus 1, right? So this becomes, by layer cake formula, exactly C iso integral over m of f to the power n over n minus 1 to the power n minus 1 over n. Okay. And so this actually concludes the inequality I wanted to prove. And observe that the same constant, unknown constant, the same generic constant C iso that I had in the isoperimetric inequality appears then in the Sobolev inequality. Okay, so this concludes also the proof. And yeah, okay, also to be more precise, let's say that this proof was done assuming that f is non-negative. I can always do it when I want to prove a Sobolev inequality. So then I can speak of this super level sets, because I forgot about the modulus of f. So let's say that I prove this for non-negative function f. Okay. This concludes this functional aspect I wanted to tell you, this beautiful equivalence between isoperimetric inequality and Sobolev inequality. And this concludes also the first lecture. So thank you very much for your attention.
Thank you very much. Are there any questions from the people in the internet? Are there questions from the people here in Mexico City? There is a question.
Hi, and thank you for the lecture. It was quite beautiful. And I have a kind of dumb question, I guess, but anyways, I'm gonna do it. If instead of considering or fixing the volume, you say that you're working on a compact manifold and you fix a homology class, does it make sense to ask kind of like a minimizer for the perimeter of submanifolds representing that fixed homology class? Does that make sense, or?
Yes, definitely. It makes sense. Now, usually, for what I know, when you want to work in a fixed homology class, the setting that people usually work with is the one of currents, right? Because then when you pass to the limits, a sequence of current, I don't know if you know what a current is, but it is again a generalization of a submanifold. And when you pass to the limit, a sequence of current in homology class, then the limit is again in the same homology class, if I am not wrong. And okay. And but the people use for this kind of question. But by the way, I believe yes, you can, for example, restrict to sets such that the boundary is inside an homology class of some submanifolds, and yes, it makes sense in general. But the point is that the theory here is just of codimension 1, right? So I am always considering boundaries of sets that are n-1 dimensional, right? So if you want to extend the theory to something with higher codimension, when still you can speak about homology classes, then the correct formulation is given in terms of currents, I would say.
Okay, and do you know if there is something done in the codimension 2 case? Because actually, this question is not just a random question. I was, some years ago, I was interested in this problem, very famous problem in four-dimensional topology, that you can always represent a two-dimensional homology class by a smooth embedded surface. And actually, the problem is to give the lowest genus possible of. I mean, you fix a homology class, and then you ask about the minimal genus of a surface representing that homology class. And I had like the impression that you can kind of like tackle this problem using more geometric methods, such as, I don't know, probably this isoperimetric story or something like that. So I'm curious if you know something, that if there is something done for the codimension 2 case.
Okay, well, I cannot give you a precise reference. I don't know a precise reference, but if you are just interested in obtaining a representation, I mean, an element of your homology class that represent the class, and it has least n-2 dimensional area among all the elements of that homology class, then the correct setting is the one of currents. So I can tell you to look for such a statement, for example, on the lecture notes by Leon Simon, okay? And the similarity you may notice is that probably for getting that kind of statement, all you need is actually the property of lower semi-continuity plus compactness, right? Because in that case, if you have those two properties, then you set your minimization problem inside your homology class, you apply direct method, and if you have compactness, which means a subsequence converges inside your space of homology class, and you have lower semi-continuity of the functional that is representing for you the n-2 dimensional area, then after you pass to the limit, you find a minimizer inside your class, and in that precise moment, you have the representative that you were looking for. Okay?
Okay. Thank you very much.
Thank you.
Are there any more questions here from the audience? No? I have a question for you, Marco. Thank you very much for your beautiful talk.
Thank you.
And I was wondering, from this last theorem, this classic theorem by isoperimetric is equivalent to Sobolev, there is also work from Cabré that shows that it is a recent work using the fractional Laplacian and all that, using fractional Sobolev embeddings. Do you know something about higher order Sobolev embeddings, which, if you know, if they are equivalent to a kind of isoperimetric problem?
Okay. But by the way, I know nothing about the fractional world, so I will not. I cannot comment about that. But
I don't either. So
okay, perfect. And here exponents are very important, meaning that this precise Sobolev embedding implies an isoperimetric inequality. Now the point is that if you apply in the correct way the Holder inequality, you may know that once you have these Sobolev embeddings, you immediately have all the other ones for higher exponents p, greater than 1. This would be the embedding for p equal to 1. But once you have this, from this you can imply all the remaining ones. For example, you can look for this classical computation, I believe, on some book by Hebei. I believe you could find it. So so the answer is, I would say that if you want to get this Euclidean type inequality, then these are exactly the exponents you want. And more generally, if you allow for another exponent p here, then it's going to be very difficult to approximate the perimeter, right? Because you need exponent 1 to get the perimeter. So I would say that these exponents are important to get this equivalence with an inequality on the perimeter.
Yeah,
and,
nice. Yeah, I was wondering because in your proof you posed a kind of Neumann problem, and you can do the same thing. Yeah, you can do the same thing for Neumann, the higher order problem, and actually Cabré's proof used a kind of Neumann problem with fractional Laplacian, and he obtained really beautiful results about about sharp constants, and so that's the question. So thank you very much, Marco.
Thanks to you. I will have a look to this. I don't know the fractional word at all, but
Don't worry.
you.
I have a question. So here for the proof of Cabret, can you also prove equality using this ABP method?
Yes, you can. You can, because precisely the idea is that what is the solution on the ball? Ask yourself, what is the solution if E is the okay? The problem here is that as in the optimal transport theory, you need to guess what you expect that it will be the isoperimetric set. So my guess is that it will be the ball. So I ask myself, what is the solution in this case if E is the ball? If E is the ball, then the solution is something like U equal to some constant times the parabola, and then you realize that this is precisely the only function achieving equality when you apply the geometric arithmetic mean inequality. So if you have equality in the end, you obtain the rigidity because you have equality in the arithmetic and geometric mean inequality. Then you conclude that your function U is x squared, and then you can conclude that E is exactly the ball. Okay. For example, you can look for the details on a survey. There is a beautiful survey by Cabret. So the key point is exactly the arithmetic geometric mean inequality. If you have equality, then you know the Hessian is constant and the diagonal matrix. Then U is the solution, and then it is precisely the solution you get only if E is a ball. So yes, you can conclude the rigidity.
Great, thanks. Are there any last questions? Okay, if not, let's thank the speaker. Thank you very much for your beautiful talk.
Thank you. Thanks to everybody. See you next time then.